We only have used half of the milk. It was mostly the milk that was. And I think when you like blend it under some mozzarella. It's like really cheesy, but like so like
No, the one that is touching all of that. Yes, are there any questions on that homework? Yes.
I had a question about part C with the equation for persistence. So I think I get for the most part that the dot product ranges from 0 to 1 based on the alignment of the two vectors. But where I get a little lost is why we divide the unit vector by, I think, absolute value.
Oh, to get the units, so it isn't squared units.
So it is a sort of units.
Yeah, otherwise you'd get like squared units, right?
Okay, is that absolute value or is that more? I've never taken linear algebra, so I don't really know the notations.
Well, I don't remember ever taking linear algebra myself, you know? So I guess it's something you pick up.
I think Norma's one has the 2 thing, or it's like the double. We talked about that in computational method.
Yeah. That's right.
Yeah, I had it last semester. We did a lot of normalization. So it was like double.
This thing, right?
Mhm. Yeah, that one.
Does that explain it, or? It's just, so that makes this unitless, just get the direction.
Sure.
So it's a unit vector, and it's a unit, well, I guess it's LP. I mean,
But then that value remains a vector, not a scalar. If you can
right, right, the absolute's a scalar.
Okay.
Yeah.
Okay.
That's the magnitude, so that's like the square root of the cross product in this. Is that right? It's just the magnitude of it. So whatever the prefactor to the direction is. So otherwise you get, I mean, I think it's just a conceptual thing about how that works. You have the chain itself has an end-to-end distance. It's got a vector, and then you take every unit on it and dot it with that and find the average of those. It's kind of like how many are lined up. Say like 3 of them, the rest were lined up orthogonal. Then you get the persistence would be like the average of 3. So 3 divided by the n would be the persistence at that point of this. Something like that. So if you can construct, I guess they construct something that like that, like the ones that are perfectly aligned, they just add up. And the ones that are orthogonal aren't. So if you had a chain that was like so many straight and then so many that way, then you also have the other angles, so it takes care of it. I guess that's more or less how that goes. All right. Any other stuff on this, or maybe no one looked at it yet, but
I guess I have to on that. When I was looking at it, on part B, I think it's like the first part, make sure I was thinking about it right. So the R value. For it, let me see what it said. It was like the first part of the question.
yeah, so there's different simulation methods.
It was essentially like speeding up the simulation by having less interactions, I think.
Oh, the
I think
distance, the
that's what-
cutoff
yeah,
distance.
Yeah.
Yeah, so if you, yeah, it's basically, you have those equations wherever they are. So let's see.
The
OPLS.
Yeah. LS. See, so you're doing molecular dynamics, you just have a bunch of rules that the thing has to follow. But one is that the bond stretches, it's just a spring, right? It goes directly stretching. The other, so that's a spring, that's just a spring constant, and that's to get the energy. So spring constants times distance gives you the force times distance gives you the energy. So spring constant times distance squared gives you the energy for just a normal spring, linear spring, right? Force is proportional to stretching. And they just use the same thing, kind of an analogy for torsion, like for twisting, or bending of the angle, I guess. Between the two, and then he has this equation. It's a dihedral, it's also like a geometric thing. Like these are kind of spring constants for dihedral orientation. So if they have kind of a fixed orientation. If they wiggle from that, there's a penalty, energy penalty they have to pay. That's kind of the idea of that equation. I don't know exactly where I didn't look up where the formality of that comes from. The dihedral, so you have two plane cards on a protein, and they're going to have an angle, so that there's two angles, one can flip and the other can flip around this alpha carbon in the middle. It's got the functional group on it. Right, so this is set up for proteins, and he flips it over to use it for isotactic polypropylene, which has like it's got two angles in it too, I guess. There's three angles in the protein, but the middle angle's fixed because that unit's planar. The peptide unit's planar. It's got the carboxyl and the amine. And they have a resonant structure.
So that ratio is referring to the angles, the distance of the angles, or would would it more so be like the distance between like the actual molecules?
This angle is like the 109-degree angle. It's carbon, 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 carbon. That's 109-degree angle. And then that can flex. So that flexes by a spring constant. And it's going to be the angle squared times angle times a constant gives you the force. Angle squared times a constant gives you the energy. Kind of in analogy to this normal spring. And then this is for the kind of rotational angle of the thing. So they call it the azimuthal angle sometimes. And here he's calling it the dihedral angle because he's using GROMACS, which is a protein program. And proteins have these cards that are hooked together with an alpha carbon with a functional group on it. Right. So the protein has three dihedrals. One's within the card, but the card's fixed, it's planar. Then the other two are the angles of the two cards flipping around that alpha carbon. So here, there's two angles in polypropylene. There aren't three angles in polypropylene, there's only two. So he's got the two angles of polypropylene, 1 and 2, of this rotational angle thing. That decides the conformation of the chain, basically. Actually, all these things decide kind of the conformation of the chain. The spring constant, these two have to do with the persistence length, and this one kind of has to do with these all have to do with the local features, I guess, really. The thing that has to do with the long range interactions is like the 612 potential, like the charges, and then these van der Waal interactions and the hardcore repulsion at the core. Right, so this 612, the van der Waal part of it can be calculated, and the 12 is just made up. That's just like, so this is called the Leonard-Jones interaction.
Yeah, that's what I was.
It's not two people, it's one guy, Leonard Jones. It's a man who took his wife's last name and hyphenated it. Kind of a rare thing, especially in the 1950s. So it's kind of a weird thing. It's one person though, Leonard Jones. So anyway, so these are just like, you have a bunch of rules and then you just let the thing go. You say like go. It's gonna, from the energy, like 1/2 mv squared will give you the velocity. So the energy, the velocity are related to each other. And that's kind of like KT, 1/2 mv squared equals KT, that's the temperature. So you have these things like dots that have these rules applied to them, which are that they're bonded together, the rotation, whatever things you want to restrict them by. And then they can also do translational motion in a direction, subject to the spring constant, connectivity, and everything. So you just pile up any rules you want, then you just say go, right? And KT, so you have to, and then you sum up all the energy of all the little dots in the system, 1/2 mv squared, the speed, gives you KT. So then you look at how the temperature behaves over time, and hopefully it starts at a high point or a low point, and then it reaches some steady value. So you reach equilibrium, right? And then you figure out from the speed of atoms, you can figure out the time scale of the system. It ends up being nanoseconds for it to reach equilibrium. But it's a small system compared to like the room or something. right? The size of the system is gonna be like, maybe like, 10 or 100 nanometer. Maybe 10 nanometer, I guess. No, so
I'm not sure if the paper talks about it at all, but is there any like impedances within it, like with with the spring equation form, or is that kind of not?
you mean impedance in the sense of that something stops something, or
Or, yeah,
impedance in the
in-
sense like electrical impedance, or like for,
Yeah, I wasn't thinking about electrical things.
Okay, all right.
Much like.
because there is like
electric and-
you can get like a frequency of the system, so you could have an impedance,
Yeah,
But basically, that's not in these equations
Yeah.
are just like Newtonian motion. There's no words, it's not quantum mechanics here. It's just like Newtonian motion of little dots moving around. You put in, and you think like, how would a bond behave? Well, it's like a spring. And if it doesn't deform much, there's some assumptions like low deformation. So you're gonna apply these things so that like this potential, so you have this Rij, that's the only place where the distances between the different dots are. Right, so basically that could go to infinity, Rij could go to infinity. So you have the box, and when you get to the edge on the right side, you come back in on the left side. And so it's like a mirror box, like particle could fly out of the box, but it's gonna come back in the other side. And the same with up and down, and somehow it works with corners. Somehow you always, whenever you leave the box, you come back into the same box. Means that your little box that's 10 nanometers can be like infinity. That's how you deal with infinity, right? So, right, so Rij could be infinity. It depends how many box lengths. When we do the simulation, you have the positions, XYZ, the velocities, XYZ, then you have like how many times it crossed the border, XYZ. How many times it went out of the box and went to another box somewhere, so anyway, so it's just a text file with all these numbers in it. And then from those text files, like I showed you that protein data banks, and then you can just create the molecule from that, so you can kind of create a picture of what the thing is from that. And there's other programs for this molecular dynamics, like displaying it. So you make a movie, do all that stuff. Like you're gonna do the simulation maybe 100,000 times, and you're gonna record an image of it every like 10,000 steps of moving the things around. Time steps, which are like picosecond time steps, And then from all those pictures, you can make a movie of like how the thing looks, like how it, when you shake and bake it, what it looks like. So if you just do like, there's plenty of those online, right? Of like Lamps video or something, like this millions of them, right? Oops. Right, that one's not very good. I don't know, maybe example. This looks like the same thing. Nope, same nothing. Anyway, you can find a video of it. I have them somewhere. Now, these are all like kind of the same thing. Anyway, Lamps is the one that we use. And Gromax is basically for biological stuff, but he's using it to get the dihedral. So it's kind of, and I think Nichols, John Nichols uses Gromax for this student in here. I don't see her, but anyway, Nichols uses Gromax. He's got a computer set up in ERC using Gromax to look at membranes, kind of bilayer membranes and things. So it also is like biologic B kind of stuff. I don't know what else. There's something about, I guess I was thinking that, so this idea of resonance, it gives you the, I'm gonna try this. So you have this way. I'll explore. All right. The idea, someone said to like use a pen, use a, all right, where's auto tune? Auto tune. So this is this double bond can go down here, so you get like this resonance structure, right? That's a peptide, and they have the alpha carbon, and it goes to another end. So this carbon, there's an H here that goes off. So that carbon, that O, that H, and that N somehow make a. That's all coplanar because of this resonance structure. So the other one that kind of an interest it has is propylene, right? So propylene has a resonant structure like that. Which means that if you come in with a free radical and try to polymerize this, then the electrons are like a balloon. You can squeeze them and they pop over to that side and you can't polymerize it because you're trying to polymerize a single bond. Trying to open a single bond, you can't do it. So there's no way to polymerize propylene until Ziegler and Nada. So Ziegler was a German guy in Frankfurt, and Nada was an Italian guy in Italy. Ziegler was a crystallographer, and Nada was like a chemist. So they invented this titanium aluminum complex material that could like basically hold on to that double bond while the free radical attacked it, and then they could polymerize polypropylene. So before that, like you had petrochemical, and then the stuff that flares out the top is mostly ethylene and like some like 1/4 propylene or something. So they would just separate out the ethylene and polymerize it and make low density polyethylene. Then in like, I think this was like 1950, these guys found out that this catalyst would hold the double bond in place while the free radicals rise, and then you could make polypropylene. So it's like, otherwise they were just burning it. It was just being torched, thrown away, right? So it's like a big, and also if you use this to polymerize polyethylene, it also holds it and it makes high density polyethylene, which is like a higher grade polyethylene than low density, right? So the whole polyolefin industry depended on these guys, Ziegler, Nada, in kind of 1955, and then that which is like 80% of the plastics used today are high density polyethylene and isotactic polypropylene. Right, so basically like the entire plastics industry was invented by these two guys, and they won the Nobel Prize for that catalyst, which seems like it's kind of a boring thing to win it for, like making plastic. But anyway, it turns out it had a huge impact for things like say you want to make a wire, right? So the coatings on wires are high density polyethylene. It's like you can't have any kind of wire, electronic wire, without this stuff, for instance, so it's kind of like had a big impact on a lot of different things. Anyway, that's also like resonant structure, like the protein, and this paper is about isotactic polypropylene. The reason it's isotactic is because when that titanium aluminum complex holds that molecule, it holds it in a perfect position every time. So it always goes in the same direction. So it polymerizes it. There's a movie of kind of what happens. It holds it, polymerizes it, then it moves over. Another propylene like fits that almost like an enzyme site and holds it while it also is holding the chain there. And then it like pops the next one. So it's kind of like a little dance that it goes through, and it spits out the polymer and eats in the next thing. So people have looked at it, made movies of it and stuff. Anyway, so yeah, that's kind of got to do with this paper, I guess, a little bit, not too much, but any other questions on this thing? Yeah. Yeah. So the dihedral pair, if you take those, let's see, if you take these cards, so if you go down the, so you can forget about the structure of a protein and just make cards, right? And they're glued together like that. And at this point, you have this carbon, which is called the alpha carbon. And it's got an R group on it, and that's the functional group that decides. Like that R group can have a sulfur, another R group with a sulfur that makes a disulfide linkage, which is like a permanent bonding. It's like an egg. That's what keeps the egg gooey, kind of. And when you whip the egg, you break those disulfide linkages, and then the thing that was like that becomes like this, and then it makes like a firm gel kind of thing, or foam or whatever, right? So any kind of denatured protein, you're kind of breaking those linkages. There's other like ionic linkages, polar linkages. There's a bunch of different functional groups that go onto proteins, and there's like synthetic proteins people have made. So there's like machines now that you can buy that will just pump together amino acids and make proteins for you. Like you can buy this machine and it'll just churn out proteins of whatever structure you want. You put in the sequence of R groups you want, and it makes that thing. And then so that you can make drugs that way. I mean, people make drugs that way. So anyway, so that was discovered kind of like in the, I don't know, 90s, I guess, when that machine that can make proteins, right? So it's kind of a big boom. Anyway, so you have these two cards, right? So whatever, the Joker or something and the King, whatever. And then so they have an angle, like there's a psi angle and a phi angle that they can spin around. Those are so hedral means face, like polyhedron is a face. So there's two faces, dihedral and angles. There's angles, it's dihedral angles, there's two of them, phi and psi. And if from phi and psi will have certain arrangements. So these things will line up and then make a larger hierarchical structure that's a sheet, right, which is called a beta sheet. Or they can have a little twist to them and then they can make a helical structure called an alpha helix, which can be like a right or left form. Like it can screw forward clockwise or counterclockwise kind of thing. And there's an N and a C end to proteins. So they have a direction. In other words, if they didn't have a direction, you wouldn't have right and left because you wouldn't know where it began and ended. Basically, one end is going to be a nitrogen, the other end is going to be a carbon. Right, so they call them N and CN. So you kind of go from, I guess you go from N to C and then see if the helix is right or left. Right, so anyway, so and if you plot phi and psi against each other, that's the Ramachandran plot. And then like if you do right and left alpha helices are like opposite positions in the alpha, and then the beta sheet will be in another position. So you can just measure these angles, which you can get from NMR, you can get it from something called circular dichroism, like how you put polar cross polars in the material in the middle, and you see how the material rotates the light. It's the dichroic ratio, and then you can figure out this Ramachandran plot from those optical measurements too. So you just get a plot of all the units of protein. You can tell kind of something about it from the statistical kind of view of how all the units pile up. So not much to do with this class, but basically it's a little bit. Proteins are polymers, but when they're in the native state, they aren't really polymers. They're like a chunk of stuff. But when they're denatured, so the functional state is normally the folded state, the solid chunk. And then the non-functional state is when they're denatured. But they found out kind of in the past 15 years, I guess, that the denatured state is actually pretty important to medical things. Like there's certain things like chaperone proteins that carry other proteins through the cell membranes and things like that. So to do some function inside your cells, and those things are all unfolded proteins, denatured proteins. So the folded ones, you can make a crystal out of them and do X-ray diffraction and get the exact structure, or do NMR and get the exact structure. And that's what that protein data bank is. So there's like millions of them that have been looked at that way. The unfolded, they're just flopping around, so you don't know anything about them. So basically that's a lot of people that work on unfolded, like actively unfolded proteins, where they act when they're unfolded. So that's kind of a big area for medical research and stuff. Anyway, so that's, I don't know. Did I answer that? That's the dihedral pair, those two angles.
Yeah.
And then there's a lot to it. Like if you look into this stuff, I mean, you might get interested in it, or you might just answer the question. That's it, So, and then figure 4. Figure 3, figure 4. So yeah, so this is the right and left helix. So polypropylene, isotactic polypropylene also forms a helix, not an alpha helix. Yeah. Oh, sorry. Yeah. Sorry about that. Yeah. So isotactic polypropylene also forms a helix, and it's got the same right and left. So like clockwise or counterclockwise screw thread. Like when this screw gets stuck, and then you drill a hole in the middle of the screw and thing you put in. Right? Anyway, that's how you pull a screw out that way. But anyway, so this is kind of the same thing, right and left helix. And then the middle part, what's the middle part? And he says what the parts are to this thing, the three kind of lobes to this. these are looking, so what those are is looking along the chain. Like he's got these kind of configurations and he's got on this thing, he has these, so he's looking at these three positions where he's put in a mismatch unit and then he gets breakup of the helicity there. So those mappings are like at different positions with respect to those mismatch things. Anyway. So any other stuff on that or?
Professor, what does dot and block mean?
Which question is it?
So in the graphs figure 2, it is showing STIPP block and STIPP dot.
Figure 2, let's see. Come on. Figure 1, figure 2. All right, so these have to do with the, so syndiotactic polypropylene, isotactic, you mean these labels, right? Is it?
Yes, but on the second graph where it is the block and the dot.
Yeah, that's when he puts the one unit that flips it. That's the dot. And the block means it's a block copolymer. So he has syndiotactic, isotactic, syndiotactic, isotactic. That's called a block copolymer. So he runs it for a while. So this isn't, that block copolymer with tacticity isn't possible to make. The ones with the little dots in them, that could be something that happens, somehow the reaction gets messed up. Right? Like somehow you're polymerizing and something happens, whatever. So it could happen. The block isn't possible to make, but you can make block copolymers using either anionic, cationic, or this raft polymerization that was in the other paper. Right? So you can use ionic polymerization, has no termination, then you can get blocks of one kind. Reaction's still going, you run out of monomer, then put in the other monomer and make the next, and then put it and run out of that monomer and put back in the other monomer. So that's how you can make block copolymers like styrene, butadiene, styrene. That's SBR rubber. It's tires are made of that. Basically, the tread compounds are SBR rubber. This kind of block copolymer. But basically, there's no way to do that with tacticity. Like you'd have to have either anionic, cationic, or raft polymerization going on, and then you'd have to be able to change the catalyst that was running the polymerization. So replace Ziegler-Natta with some other catalyst that doesn't exist. Or maybe there is. Let's see, the iso and syndio, in some polymerizations, you can change just by changing the temperature of the reaction. Like if you run this one at minus 200 C or something, and then run it at room temperature, and then take it back to minus 200, that's possible, I guess. But so it might be possible to do that, but basically no one's made block copolymers like that, I don't think. So that's what he means by block. Dot is like you just put in one unit, mismatch unit. I think the point is, even just putting in one mismatch unit, you can get this huge discrepancy in the behavior. And then the block, which is the black one, you see discrepancy where it changes and the persistence. It's kind of interesting what they did here. I mean, academically, it's interesting. Is that okay? I think if you
Yes,
read
Professor.
it, he says that, but basically you have to read carefully what he's talking about and kind of know what things mean too. So anyway, any other questions on this thing? So, all right, so let's see. That's okay. So anyway, I wanted to go down, I think it's like 87. I had a sheet with the numbers in here. All right, yeah, it is something like 87. So I wanted, let's see. So we've done most of this stuff. That thing we haven't done, but I don't think it's that important. Then I wanted to talk about polyelectrolytes, which proteins are polyelectrolytes because it has the peptide unit has a carboxyl and an amine unit in it. And the carboxyl's kind of negatively charged and the amine's kind of positively charged. And then also the side groups can be polar too, right? So that would be like, this is polyacrylic acid, which is like the stuff for superabsorbents in a diaper. But if you polymerize that, you make a sodium salt of the hydroxyl, and then you can, and that's like absorbs water like crazy. Like it'll absorb something like 1,000 times its weight in water. Like it just swells up like crazy. So if you make a network of this, it just makes a gel that's almost all water, right? So you start with a little bit of powder, like a salt shaker, shake it in the glass of water, then it just turns into jello, right? So it's kind of a magic trick. You can do that yourself at home if you have a diaper, like a disposable diaper, just cut it open, shake it a little bit, and a white powder will come out. And it's all this acrylic acid, sodium acrylate, super absorbent. So if you want to, you can put that into your plant pot or something. It will keep the water, so the plant, you don't have to water the plants as much. In fact, they put it in, like if you buy potting soil for cactuses or something, it has that in it. Then farmers actually spread it out on the field to do the same thing, like keep the water in the soil. So anyway, it has some uses like that, and it's got a lot of people are interested in it to make hydrogels for various reasons, you know. Anyway, so that's kind of a popular, so it's called a weak polyelectrolyte, and just the peptide unit would be kind of a weak polyelectrolyte too. But if you add alpha carbons with polar groups on it, it can become a strongly charged polyelectrolyte. So this would be like, so this is sulfonated polystyrene. So somehow involves sulfuric acid and polystyrene. And you can make the sulfonated unit on it, right? And that's a strong polyelectrolyte. So it's kind of separate into the two types. Usually people are interested in the weak polyelectrolytes. This thing will just phase separate into two domains, like a polar, and it isn't totally sulfonated. So the non-sulfonated parts aren't polar and the others are polar. So they separate out. And these can be like, make like ion conducting zones and make a separator with it, like an electrolyte separator where ions can transport through that part, and the other part kind of gives it structural integrity. Right. So there's a lot of uses for strongly charged polyelectrolytes in the electronics industry, like batteries and fuel cells, stuff like that. Right. So anyway, and these are kind of biology, more or less, like the weak electrolytes. So these phase separate, that's kind of the end of the story, except no one really knows what structure it makes. And then there's a lot more like science considering about the weak polyelectrolytes. So anyway, this belongs to this category of like our, this is the Debye-Huckel potential, that's the Debye screen length. This is the concentration of counterions. So you'd have like, here would be hydrogen, but it could be sodium salt of that, so sodium ions, then 1 over the square root of those. So the more counterions you get, the shorter the screen length and the shorter the distance that you can observe the charge. And the energy between two, including with the counterions there, decays exponentially. So this thing just kind of has an exponential decay. And then it's also reduced by 1 over r here, just kind of like a charge thing. Charges, the force of a charge is 1 over r with distance, and this takes care of the exponential decay and screening. But if you have two charges, the potential between them without the screen is just 1 over r. Like d would be infinity, and then this thing would go to 0 somehow, or go to 1. And then rd would go to infinity if you had no counterions. With counterions, this exponentially decreases the natural thing of two charges, which is 1 over r. Right? So anyway, so that's the potential between these units. So within the structure, you have like how many, like the density of units along the chain, charged units, right? So you have like a distance a between the charged units. I mean, it could be 1 mer unit apart, or with this case, it's going to be like many mer units apart, because you just take polystyrene, sulfuric acid, it's not going to sulfonate all the units. So you get some of them. So some distance a between them here. Here, the distance a is like a mer unit long. So you have a new distance akin to the persistence length that's thrown into these things. Then you have another distance that's thrown in, which is a screen length distance. Then you have the natural persistence length. There's like 3 distances that somehow match up with each other in a polyelectrolyte. So you have to figure out how those can balance out. And also, so there's also some energy balances with these things. So anyway, I mentioned before, there's also this number, the Bejerom length. right? Which is like so you have a charge interaction and the things are moving around by KT. So some distance you can go out where the shaking around by KT is stronger than the attraction of the charges, which sounds like the Debye screening length too, but it isn't. It's not the same. Okay, so the difference is that so above so the Debye screening length is larger than the Bejirum length. So that means when you can go above the Bejirum length and still be feeling the charge, still have an interaction between the two charges. So the difference is above the Bejirum length and below the Debye length, it's like a mean field interaction. In other words, there's no direction to it. And when you're below the Bejirum length, there's a direction to it. So you have a point where there's no effect of it at all. Like you can't see there's another charge at all because of the other counterions are in between, you can't feel it. That's the Debye length. There's a length where the thermal motion kind of randomizes the interaction that you have. That's the Bejirum length, right? So you have, if you say like you hear a gun go off, and then you're gonna like run away from the gun, right? Because you think it's safer to go somewhere else. Or you can be in like a battlefield where there's guns going off all over the place. And that one gun going off has no effect on you at all. So basically you're just it doesn't make you run one way or the other. You don't even really hear it, right? So that's the Bejirum length. That's like that's the Debye length where you can't sense the other one. And then where you can hear the direction of it is this Bejirum length. It's like when you're closer, you can say the gun's right there, I need to run away. Right, so it's kind of like two things that can happen with a gun, I guess, in a war situation. Right, so anyway, so that's kind of a picture, or you could do something like have the kid crying for his mother or her for her mother or whatever. And then you can be a distance away that people are shouting, but you can hear the kids still shouting, don't know which direction it's from. Right, and then at some point you can't hear the kid crying at all. That's the Debye length. So the point where you can't tell which direction it's coming from, but you can hear someone screaming, that's the Bejirum length. So they're subtly different from each other, right? So and they're related to each other somewhat, but anyway, so you can get into this nitty-gritty business. So if you look at this kind of potential, this is a correlation function. So it's like if you start from one thing and then say like how far to get to another thing, right? And then if there's a shell of the things around it, there's a peak in this, and then there'll be multiple orders of that peak, right? So you can say like the Bejirum length is where that oscillation becomes flat, and it's like a mean field. Like the field is still there, like it's not zero, but it's so far away that you can't tell kind of which direction it is. And then when you're closer, it's kind of like this is like within the Bejirum length. And the Debye length would be where this thing would disappear. If you want to look at it in terms of this, I forget where that's from. It's from someplace. Maybe they invented that, I don't know. But so anyway, so that's kind of the picture of this thing, right? So we had the Debye length already. So these are the kind of complications in polyelectrolytes. So, I mean, not that there's not enough complications for this persistence length thing already, but so you have to consider the counterion concentration. And then the chains themselves, if it's a polymer chain, so you're looking at one unit interacting with another unit. So the other monomers on the chain also all have charge. So those add into this N, like they count as counterions. So it does become a little complicated. You have one unit interacting with another unit, then there's all the other units of the chain that are acting as like noise, kind of like Debye noise to give you the screen light. And then the counterions are also adding in that way. So you have like two things. Then what's this? Counterion condensation. So if the counterions, so there's a balance between counterions like diffusing around, and then this attraction between the plus and minus, like sodium and the hydroxyl group, right? So it's basically those two things have to balance out. If the attraction gets to be too strong, then the counterions collapse onto the chain, and you get such a high counterion concentration, the Debye length goes to zero, right? So if the counter is relying on the counterions like shaking around, so that they don't just collapse onto the chain. Say like the moon going around the earth. If it stops, it'll just drops, right? So you have to have this kind of like KT thing, keeping the moon moving, to end up with kind of a balanced position there. But if somehow the temperature drops enough, those counterions will just collapse down and it isn't a polyelectrolyte anymore. And then it's not dissolved in water, for instance, it just fall out, right? So that's called counterion condensation. It's another issue that shows up in this thing. And then the chain ions contribute to the device screening. And then there's some kind of complications that can happen, like polyelectrolytes can form structures and things, kind of like surfactants, right? So like PEO, PPO can form micelles and things if you let it. So anyway, there's a few. This is, I forget where this is from, but could be from that the Penn State book, that Polymer Physics thing. Anyway, this is kind of the picture. So you have those three numbers. You have persistence length, and then you have your raw persistence length, and then something called an electrostatic persistence length. So these charges are going to force the chain to try to straighten out. That's the idea. So that something like a protein or this hydrogel, those things are going to have like almost complete persistence. Like they're just stretched out. DNA, those things have like huge, like up to micron persistence lengths, like huge, totally huge, thousands of times bigger than a synthetic polymer because of this charge thing going on. So so you have to consider like what's the relationship between these numbers, these three numbers, like spacing of the charges on the chain, the persistence length. So if the spacing of the charges on the chain is bigger than the persistence length, then they don't affect the persistence length. But if it's smaller, then they can affect the persistence length if the persistence length is smaller than the device screening length. So you can figure out how that works. But basically, that's the relationship you need to have this electrostatic persistence length show up. And then you have the sum of the two gives you the total persistence length of the chain. So anyway, so this is how, I think this is from, well, there's a paper by the guy Cates, the British Nobel candidate, whatever, right, from Cambridge. And then Evans is a pretty famous simulation guy too. Anyway, this is a picture of kind of how these things fit together in terms of an energy balance thing. So this is just your from thermo, you know, so you have, except that the volumes you're talking about are so you have a cylinder, which is basically the chain, and the cylinder is like the kind of the, well, it's the persistence length times kind of a diameter. So it's saying like, what's the persistence length? You're trying to get that in the end, how the persistence length is increased by the electrostatics of this thing. So you have like two volumes that have to do with condensation of the charges onto the chain, right? So you have like so the volume changes. This volume of the chain changes because of condensation of charges into the chain. So you have this is just a standard thermo equation, like internal energy is the PV work and then the heat. So if you say the heat's 0, you have just a PV, and if you integrate that thing, you end up with log of V2 over V1. So that's just like straightforward thermo number. And then this thing has to do with the attractive potential of the chain. So like the charges, how the charges want to get attracted to the chain. So the Debye-Huckel potential. So you're going to use the Debye-Huckel potential equation, which this is the derivative form of it. It's the same as the other equation for the Debye-Huckel thing. Except I don't see anyway, it's a charge squared divided by the charge spacing. So that's like the charge density. That becomes rho. Like how many charges per distance along the chain is E over A. So that's rho. E's the charge, E squared is related to the energy. And then you end up with this, the distance. So you end up with this same differential, like except it's in terms of the charge spacing along the chain, which ends up giving you also the volume ratio log thing. So if you equate those two energies, this is the electrostatic. This is kind of the more or less the entropic, I guess, part of the thing. So you relate those two together, you equate those two energies, then you find out that you have this parameter falls out of that U, which is related to the charge to the temperature, like the Brownian part, and then the charge on the chain. So this is the attractive potential that's making the chain charges collapse. And then this is the Brownian motion that's making them not collapse, making the counterions not collapse. So if this is smaller than 1, then you get dispersion of the, in other words, if KT is larger than the charge, you get dispersion into the solution of the counterions. And if it's bigger than 1, then you get condensation on the chain. So this U parameter becomes the number of importance, like a parameter of importance to a polyelectrolyte. And they just find out for any chain that's in solution, you have this U, magic U number, which is the charge density along the chain. So like charges of the units divided by A, so linear density times E over this KT. That has to equal 1 for the charges to be balanced with the chain in like a natural situation, right? And then you get, right, so this is the kind of language that people are using. This U parameter shows up in papers. Like you'll see that in a paper. So maybe if I find a polyelectrolyte paper for this week, then we'll see you. If not, you'll never see you again. You know, it's like one of those things. This U parameter is in every polyelectrolyte paper. So that kind of shows like where the charges saturate at this U equals 1 number. It gives you this effective packing length of the charges on the chain. So what else is in here? So summary of polyelectrolyte, probably good to say. So there's 3 numbers: charge spacing, Debye length, and then this bare persistence length. And then you end up with this parameter U that decides whether you have charge condensation or not. If you have charge condensation, it's not a polyelectrolyte anymore, because it's basically so much screening that you don't have it anymore. So what else is in here? Just jump. All right, then there's this business. So at this scale, like on the chain scale, so we have like Kuhn length, persistence length, and then there's 2 other parameters that show up in melts. Like once you get, so, that's the other thing. Oh, all right, sorry. That was slide 111 or something, I think. You don't need this stuff. I put something else in there. Someone said, like, what is a melt? Like, what is a polymer melt? And I just said the magic word, it reminded me. I put another slide in here somewhere. Here. All right, so if you have an isolated chain, so I mean, I made it branched. So if you have an isolated chain, then that's called dilute. Like, so you have it so dilute, it's like less than 1% concentration, milligram per milliliter, right? So that's so dilute that they're just isolated chains. And that's how you want to analytically, GPC, whatever you want to do is going to have to be done in the condition. So you can see 1 chain, right? And if you look at the scattering, so you have, if you get to the size of the chain, then beyond that, you just see constant, it just has a constant intensity. Then when you get to the size of the chain, then you probe within the chain, you see it's a 2-dimensional object. And then you get to the primary structure and you get some either power 1 or power 4 out here. If it's a rod, it's 1. If it's solid, it's 4. In this case, it's 4. That's the persistence length, that's the coil size, an inverse size. And this is I divided by concentration. So as you increase the concentration, then at some point at a side, you can't see the individual chains anymore. So it's kind of like the fleece. So you can't see a fiber of the fleece, right? You just see the fleece. So you can see, but what shows up is this screening length of the thing, this length of the holes in this thing, right? So that screening length shows up there. Then above that, you just see a constant intensity, right? And then you can still see, if you zoom in, you can still see fiber structure. When you can still see fiber structure, that's called semi-dilute. So this is dilute, that's called semi-dilute, right? And if you fire up more concentration, then it becomes smaller and smaller holes. This size goes to higher Q, this 1 over size. And you screen out more and more of the structure. So this is structural screening, not charge screening, right? And the pore size gets smaller. And finally, you reach the persistence length. or, right, or you reach the bead size here. And at that point, this becomes a melt. It's essentially a melt. There's no more porosity in it. There's nothing else to see. All you see is just like the solid thing. Right, so if you pull out all the solvent, that's like really a melt. That's just like a packed together of a bunch of wormy chain things wiggling around, right? So that's like a polymer melt. So there's no solvent in it, right? And there's no hope of seeing one chain. I mean, unless you go in and deuterate one of the chains and then look at it with neutron scattering, and you can see one chain in that mess if you can somehow light it up or fluorescent tag it like the other guy did in that microscopy thing, right? So that's the idea. You have dilute, semi-dilute, right, and then concentrated. So anyway, within this semi-dilute, so what's going on here? So if you say like so if you shoot a beam of radiation through and then you get scattering from it, there has to be a contrast that gave rise to that. And it doesn't like there's no contrast in this last one, right? So the contrast is this, everything's moving around KT. Like say you have a glass of water, there's contrast if you shoot a beam of light through it, you get some scattering. Okay, it's because the water atoms are moving around KT and they're clustering like in one region, then they're dispersed in another region. So you have like all around, you have clustering and dispersion. And it's dynamically happening, right? So basically KT is kind of forcing them to crowd together. And the thing that makes them push apart is there's a pressure that things create themselves, which is called osmotic pressure. There's a pressure, it's just like atmospheric pressure. Like if you push things in, you get higher pressure. So that pressure makes those water molecules want to spread out. So the rate that this thing drops, so it, like if you divide intensity divided, because the concentration will just go up the higher the concentration, divide by concentration. Then the rate at which this thing drops with concentration, this is going higher and higher concentration, that's related to the osmotic pressure. Like what is the osmotic pressure of the system, which is basically a measure of like how the thing's put together. So just doing a concentration series, if you can measure this intercept, then you can get this thing, the osmotic pressure of the thing, which is the first derivative of the free energy. And if you do a viral expansion of the free energy, it's the second viral coefficient that you get from that. Right, so you directly get the second viral concentration series thing. All right, so anyway, that's kind of a long story to what a melt is. It's got a lot, so there's a lot of physics and whatever understanding involved in what it's a dilute, semi-dilute, concentrated, and then kind of like concentrated is the same as melt. Right, so that's kind of how this picture looks of the thing. I should have mentioned that. I never realized that that's like pretty important to mention straight up at the beginning. So everything we're kind of looking at first is dilute. And then finally we get to, except when we do rheology, then it's concentrated or melt state, right? So all the rheology, the G prime, G double prime is like over here. And all the analytic, like scattering, is over here, right? So the two things are kind of separate, in a sense. It's the same chain. So basically, so we'll talk about what happens later on between those. But all right, yeah, I successfully wasted enough time probably here. But yeah, so next time I'll go through these other measures like the packing length and the packing length and the other thing, whatever it is. There's two other numbers, tube diameter. I'll mention what those are. It's on the same size scale as the Kuhn length, but all right. So email me if you got questions on that homework. Just email me. I'll kind of tell you the answer. All right. So all right, let me quit there, I guess.
Sounds good. Reactions. I don't think you can make it right. I have a doctor's appointment for my liver today, but I should be able to go tomorrow because I'm meeting that one professor, so can that a lot, and I'm going to assume I'll be done. Yeah.